Welcome to the new episode of Dat-a-science, and get ready to ask yourself the questions of chaos. We will be delving into entropy, what uncertainty is, what cross-entropy is, some weird mathematical names like KL Divergence, and a whole new world of compression engines, predictors, and classifiers, and getting into the geeky part of machine learning. But here's a caution symbol, a caveat, if I may. We will not be getting into the calculations and actually calculating KL divergence for a few problems. I think we have loads of resources for that. We will just be getting the intuition and deriving a few formulas related to entropy, divergence, and we will be primarily focused on the implications and the applications of these technologies. So stick around and get ready for the adventure for today. And just ask one question as you put your thinking caps on. Dat-a-science, bro? You see chess here? Well, it's exactly the depiction of what entropy would look like. A chaotic board with pieces all around the place, you don't even know what to move next. That's exactly what chaos looks like, right? And the more the chaos, the higher the entropy. And that was the crux of using that. Genius of me, right? Let's go through the next slides and try to understand what's happening. Story time. Are you all ready? Well, a child says, "Mom, will it rain today? I really want to play football. The report says it'll rain with a 50% chance. What do you think? What does that translate to?" And the mom is like, "Well, that's not a lot of information. It's really tough to say using this." And the child goes crazy. He is disappointed. And now the child is really determined. The discussion continues and he says, "Well, if you don't want to answer it that way, I've gathered more information for you, and now you will have to answer." He says, "It will rain with a 33% chance, it'll be sunny with the same amount of chance, and it will be cloudy just the same. So what do you think now?" And the mom is like, "No clue." The child is devastated. Now let's analyze this rather innocent looking discussion and try to understand what caused so much of uncertainty. The probability of all the events occurring has always been the same in both of the cases. When there were two candidates, the probability of each event was 1 by 2. And it lowered down to 1 by 3 once the number of candidates increased from 2 to 3. This also called chaos and randomness or high entropy. Whenever we have a huge amount of ambiguity and things that are very likely occurring together in similar probabilities, that is considered to be a case of high entropy. Now, if God helped with girlfriend problems, now don't take me wrong, I think these are wonderful, wonderful beings. And we're all blessed to have a significant other helping us out through the journey of life. But there are a few problems that can grow a little annoying at times. And it's really difficult to predict how your girlfriend would be the very next moment, let alone the very next day. And only if we had a system to actually predict how she would feel, that would be amazing. And thank you God, now we do have such a system. So now what does this system do? Your girlfriend can be happy with a 0.5 probability and angry with the same probability. The God says, "Hey, you know what? Be ready to face her wrath. It's really not going to be pleasant. And the probability of being angry is something that's going to come true tomorrow, or the next moment, or the next time that we are talking about." So now that has reduced our uncertainty by a factor of 2. Initially we had 2 possible solutions in mind, and now we only have one, knowing which one it is going to be. Another important thing to notice is only if God said 0 or 1, we would still know which one it is for the next day. And he could then help other boyfriends suffering from similar issues. rather than sending a "be ready to face her wrath" sort of thing. it could have been just delivered in a 0 or 1. Well, this is clearly not all that dramatic, but it still does the job. And so we learn that only by using one bit we can convey the message and reduce the uncertainty by 2. God though, we only wish we only had 2 moods. But unfortunately, or well, honestly, fortunately, we have a lot of them. But as statisticians, we really wish we had 2 moods. Because that was easy math, and now it's not. Let's say we compress all of our moods, a lot of them, into 8 basic categories. And God had to tell us which one it's going to be. So if he had to pick one, he would be taking our uncertainty down by a significant amount, which would be by a factor of 8. But to do that, he also needs a lot more information that he would need to pass on, which would be, since it's binary, the log with a base 2 of 8, which is 3 bits of code. Now very shortly I'm going to debunk this theory and say, well, this could be done using less than 3 bits on average. And we will prove it, but before that we have an important task at hand. So here we're trying to understand the probability of being happy or mad is different. And the God still tells us that she will be mad. And well, this is not the same as it was before, because initially when we saw the example of a binary situation where we only had 2 possibilities, happy or angry, we were dealing with equal probabilities. And now it's more likely that your girlfriend will be happy the next minute or the next time that we are talking about. But then if the God says that she will be happy, he's literally not doing a lot of work. I think that already was a little biased sort of thing. But at the same time, if he says that she will be angry, now well, that's an unlikely thing coming true. So I think that's a significant decision. That's a significant prediction that God has made. And when he does that, he actually reduces our uncertainty by not a factor of 2, but instead a factor of 4, using exactly 1 bit, because the information is a binary anyway, since there are only 2 possible outcomes. So whenever there is an imbalance, the entropy reduces in comparison to the uniform distribution. And this also takes us to one of the most important deductions in the information theory. When we reach out to deductions, we intuitively understand a few things. The probability of an event occurring contributes in inverse log order to the final entropy. And this means that if you really want to increase the entropy, if all the events are equally likely to happen, the entropy will be maximized. But we really want to live a life of simplification. We want the entropy to be as less as possible. And so, we really want to reduce this entropy. But to reduce something, we ought to know what the formula of that certain thing is. And in this case, we are having a few hints towards the same. We know that log of 1 over pi is directly proportional to the entropy. Now, log of 1 over pi can also be written as negative log of p of I, for the ith event, that is. And this is just a property of log, or one of the logarithmic rules. And there we have it. As Wikipedia would highlight, h of x being the entropy of a distribution x can be given by the formula mentioned down here. One very natural question that should come to us is, why really are we using binary? I mean, if we're using log, we can definitely use the natural log or the log to the base 10. The simple answer to that is that this is information theory. And information theory basically deals with transmitting and receiving of information. And that is what we essentially do all the time when it comes to data. And how do we transmit and receive this information? In binary code. And hence we use the log with the base 2. When it comes to information theory, there are a few interesting remarks that I would like to put forward. The forefathers of this wonderful technology are Claude Shannon for his Shannon-Fano code, which was a remarkable work, and also David Huffman for Huffman code. These people prove to us that when you want to reduce the uncertainty by a factor of 8, the average length is not necessarily 3 and it can be lower than 3. How? Well, we will know more about this when we learn about cross entropy, which is literally just the next slide. Well, what exactly is cross entropy? It literally is just the expected length. So using a certain coding mechanism, when we have a distribution of a property or probability of a certain distribution, we really want to make sure that that is sent well and also received well, causing minimum error and maximum efficiency. So this cross entropy is nothing but the average length of information in bits that we will have to send through. We initially understand that the most frequent or probable outcome must be given least bits, so that we know that if I have to transmit a 0 90% of the times and I only use a 0 to transmit that, my machine will be transmitting maximum data using minimum energy, which is great, right? The average length of cross entropy is given by the probability formula, where the length is the xi part of it and the probability is the pi part of it. And now, according to Wiki, the cross entropy can be defined as the formula mentioned below. The cross entropy can never be less than the entropy. Now, this is a wonderful fact to know, and I think we've got a bunch of these facts. In most ideal case, they may be equal, but it is never less than the natural entropy or the entropy. Suddenly, we are interested in the difference between the two. And why is that? Well, the reason we are interested in that difference was brought to us by Solomon Kullback and Richard Leibler when they were researching about the distributions themselves. Well, the difference in the two distributions often tells us how away are we from the real distribution. So if the real distribution is sort of Gaussian and we expect it to be a Poisson distribution, the KL value will be really high, and that will indicate us that, well, you're far away from your target. And if the KL value is low, we are eventually making it close to the real distribution. So the smaller the difference, the better our estimate is of the real distribution. And so kudos to these great scientists that brought us this formula. So now let's just derive this formula, which is not a very tough nut to crack. We have the two equations here right in front of us. The equation 2, which is at the bottom, and the equation 1, which is at the top, both in green. We just subtract 1 from 2, which is nothing but just equation 2 minus 1. And remember one property of our good old friend log? Log of a minus log of b is actually log of a over b. And we use the same method to find the KL divergence between the distributions p and q. Given that our target distribution is q and the predicted distribution is p, it is nothing but negative summation, and this is for a discrete distribution where all the values are discrete, by the way. Had it not been discrete, we would have used integral instead of sigma or summation. It would be a negative of p of x log of q of x over p of x, which can also be rewritten by taking the negative sign inside the summation and changing the numerator and denominator, because it will be just 1 over q of x over p of x, which is nothing but p of x over q of x. So there we have it. Remember, friends, what stems out of chaos is beauty. And we will be talking about these beautiful applications of KL divergence, chaos, entropy, and everything related to it. We are now delving into the area of classification, regression, compression engines, machine learning in general. Let's first take a look at a classification problem where we widely use KL divergence. And the first one is that we have three possible outcomes and we have a small sort of array of it. One outcome is an airplane, a train, and a cat. And we show our lovely algorithm the picture of a cat and ask what it is. Well, we for a fact know that it's a cat. And this is supervised learning. So we also have a similar data set with all the three outcomes with a 1 mark next to cat and zeros across every other thing. And when we compare the two of these, one is the prediction and one is the real outcome, we use KL divergence. To know how close the prediction structure is to the real one, or the prediction model is to the real one, we use KL divergence. But when we put the matrix to check it, we actually put in cross entropy. Oh, wait a minute. Didn't I just say KL divergence and then I switched to cross entropy? Agreed that these two are similar, but these are not essentially the same. Well, in this case, they are. Right? KL divergence essentially is nothing but the difference between entropy and the cross entropy, which is the predicted length. In this case, what do you think the entropy is? 0. Absolutely 0, because we exactly know that it's a cat. And even if we go by mathematics, it's 0. So essentially, cross entropy minus entropy is KL divergence. But when entropy is 0, our KL divergence is actually exactly equal to the cross entropy. And hence, cross entropy plays a crucial role in multi-class classification. Let's jump to something else. Let's jump into the world of autoencoders, and specifically in this case, variational autoencoders. Here in the middle layer, we use a distribution. And this distribution, guessing by mu and sigma, guess what it would be? Well, in most cases, a normal distribution. And this normal distribution has a mu and a sigma. So we use KL divergence to check the actual and the predicted distributions and to see how similar or different they are. And this is coming to the bleeding edge technology of variational autoencoders, which by the way are also stepping stones for generative adversarial networks. So essentially, out of chaos, we've created beauty and implemented it in the bleeding edge technologies. That is what science can do to you, and especially data science. Or well, just dat-a-science? Well, for this case, it actually seems like it really is. If you've really enjoyed this video and made it so far, make sure to drop a like. Please subscribe to the channel, because we are really in the initial stages of this and we really want more subscribers for this sort of quality to come out. And please share it with your friends. I will be dropping a few research papers, one written by myself and a variety of scholars writing these research papers across that'll give you an in-depth analysis and understanding of KL divergence, where you can specifically go and understand the calculations behind it. You can probably do the math, delve in a little deeper in the concepts, or anything you like. I will have it all in my description. Please make sure to like, share, and subscribe. Thank you, and have a wonderful day, week, month ahead.